Thank you very much for having me here, although it should really be Sebastian Ullmann standing here, who actually has done most of the work that I'm going to talk about. So this was all in the attempt to use a mesh code, the repo code, for simulating the plunge-in and maybe a little bit of the phase after this for common envelopes. And we actually introduced the numerical methods already, so I start with one major part of Sebastian's work. It was actually to define setups for the simulations, and as I mentioned before, so the fundamental issue that we have here is usually that we have to map a stellar profile from a stellar diffusion code where hydrostatic equilibrium is in the model by construction to hydrodynamical code where hydrostatic equilibrium is just a special solution, but it's not explicitly enforced. So therefore, we have to care about these things, whether the profile is stable over long time scales that we set up in the hydro code. To follow the common envelope simulation, we need it to be stable over many dynamical time scales. This is hard because the envelope is only loosely bound, and we have a wide range of temporal and spatial scales. And now, the scale problem, as already discussed many times in this workshop, is actually usually addressed by replacing the core of the giant star with a point mass that interacts only gravitationally with a certain gravitational softening length. If you actually keep the rest of the envelope as taken from the stellar model, then this is not really a resolution-independent approach. So therefore, Sebastian actually tried to develop a procedure where the inner part of the star is really cut out up to a radius of about the gravitational softening length and replaced by a stable structure that actually at the same time guarantees that the outer profile from that stable structure would look very similar to the original envelope of the star. And this is achieved by solving this modified Lane-Landon equation with the potential of the point mass representing the core being included. And then we stitch these two profiles together with the inner profile with the outer profile of the stellar envelope at the cut radius in a smooth way, and in this way one can actually construct in a reliable way resolution-independent giant models for these simulations. Now the next problem is then the question of how you map into the hydrodynamical code, which may have a different equation of state. So many of the published simulations actually use an ideal gas equation of state, whereas the stellar model was usually computed with, say, the Mesa equation of state, including recombination effects and so on. So that means that the profile that we map is not necessarily in hydrostatic equilibrium. Therefore, only a few base quantities are mapped, density and pressure. But this actually then guarantees mechanical equilibrium, but not necessarily the same thermal structure as the original star. So convective properties are not necessarily retained by this mapping procedure. So you map, for instance, from a Mesa model with a convective envelope to a hydrodynamical code with an ideal gas equation of state, then the envelope will not be convective anymore. So therefore, we actually use a different base quantity for the mapping and the hydrostatic reconstruction, and that's the difference between the temperature gradient and the adiabatic gradient. So it's an equilibrium for convection, and this actually then guarantees that we have the same convective pattern in our model star. Now, of course, all this doesn't matter if you actually use exactly the same equations of state in the stellar evolution and hydrodynamics code, but still, this method actually allows you to arbitrarily change the convective behavior of the star by just changing the difference in its gradients. Now, then in the end, we have to construct a 3D representation of the 1D stellar profile, and the rather flexible unstructured moving mesh of the repo gives us different choices. Sebastian actually tested a number of possibilities here. Our method of choice is a Hughes tessellation on spherical shells, but you found that it actually has little effect on the final outcome as long as we have the moving mesh actually doing its job, and this adapts to the geometry. So therefore, this is not so important. But if you actually work on a static mesh, this actually may have an effect. Then mapping from a hydrostatic stellar evolution code to a hydrodynamical code. The hydrodynamical code usually has low resolution, and this actually leads to discretization errors and spurious velocity fluctuations will occur, and maybe the star also starts to oscillate, and this is usually then damped out on the certain time scale. So we also have to do this damping procedure, but of course one wants to avoid to do this damping too harshly to the star to not change the profile. So therefore one can actually think about criteria of the resolution that we need in order to actually keep these spurious velocity fluctuations from discretization errors as low as possible. And so Sebastian worked this out based on work by Mike Singali, and you can come up with a criterion that gives you the Mach number of the spurious velocity fluctuations due to discretization errors, depending on what kind of Riemann solver you use, and depending on how well you resolve the pressure scale height in your stellar model. Or you can actually then ask the question, so how well do we have to resolve the pressure scale height to keep the Mach number of the velocity fluctuations below a certain threshold. Now with these setup models, Sebastian has performed common envelope simulations, and so its standard showcase example is a 2 solar mass giant and a 1 solar mass companion star. The companion in many of the simulations was placed at the surface of the red giant, but Sebastian also tested different other initial setups. In the first set of models, we modeled pure hydro with an ideal gas equation of state, so that means no magnetic fields involved and no ionization effects. And then the simulations look like here. So this is a cut through the xy plane, and you see the two cores of the stellar cores orbiting each other, indicated by the plus and plus here, and the outer envelope actually sort of develops this complicated morphology. This is the overall outcome of the simulation. So we followed the evolution in this particular setup for about 80 orbits, and only 0.1 solar masses of the envelope material, that's 8% of the envelope, was ejected, predominantly in the first 3 orbits. And this is how the distances actually, the orbit distance changed, very similar to what other simulations find as well. Now one can characterize the evolution of the envelope in different phases. So the first is the rapid plunge-in phase in the first orbit, that's shown here. So this then leads to an eccentric orbit of the 2 star cores, and the shock from the companion star reaches the inner part of the envelope, and around the red giant core another shock forms. And most of the material that finally gets unbound is already ejected in this first orbit. And in the second orbit, the red giant shock or structure takes over the tidal arm of the companion, and later on, after a few orbits, the layered structure forms. Shear flows in the outer layers, where the flows are subsonic, lead to carbon-Helmholtz instabilities, and you see these carbon-Helmholtz features appearing here. Later on, the carbon-Helmholtz instabilities become stronger, and the spiral structure tightens, and then finally the instability in adjacent layers starts to overlap, and we form large-scale instability patterns that now dominate the entire morphology of the envelope, but in the center, still the spiral structure is generated by the 2 orbiting cores. Finally, when we end our simulation, the spiral structure is completely washed out by the instabilities. The cores are still well resolved, and flow between them is smooth. Now, we take this as the onset of convective instability. This is analyzed according to the Stolberg-Cournot criterion. The orange patches here are unstable to that criterion. You see that they are found all over the place, and this actually indicates convective instability. Now, we've also done NMAT simulations with a slight weak magnetic initial field, and followed the amplification here. This was discussed before. We have different phases where initially a strong amplification happens around the companion star, then a slow amplification in the secretion stream that has formed around the companion star. And finally, we get a saturation when the magnetic field is dispersed over the entire envelope, and we end up with magnetic field strength on the order of 10 to 100 kilogauss. This is just a wrap-up of these things. So the dynamical impact is rather small. We get only slightly more material ejected than in the non-MHD simulation, and the magnetic field strength that we find is still too low to explain magnetic white dwarfs. And it's also not clear how to anchor these magnetic fields, rapidly changing magnetic fields on the white dwarf surface. Now, Sebastian in his PhD thesis that was cited before already had some simulations that included recombination energy by putting in the Opal equation of state. This assumes, of course, as we discussed, local energy deposition. What we find here is that compared to simulations with an ideal gas equation of state down here, we get much more material ejected with the Opal equation of state. Here are different criteria for evaluating which part of the material is unbound. So the pink line and the yellow line are just evaluated according to the kinetic energy of the material that we have. And the blue line here is a lower resolve but longer simulation that's a custom carried out. We actually get a substantial ejection of material. In this case, recently, master student my group looked into different primary stars, HB stars. The challenge here is, of course, that the envelope of these is much harder to stabilize numerically. But as my master student did some simulations, is the outcome with different Q values, and you see again that we get a significant mass ejection only if we take the Opal equation into account and recombination effects are considered. Okay, so that's it. I think my time is up. Conclusions, well, this is all work in progress. We are currently working on including radiation transfer to see whether the assumption of local energy deposition is time for a few questions.
So I don't think we should be allowed to leave this conference without having made come to an agreement about the B fields. So yesterday, and I'm not saying solved it, of course, but the work of Sebastian shows this specific amplification and the fact that it's not dynamically important. It all makes sense. You wrote there, but this is not the Regos and Taut field. But yesterday I was having dinner with Rüdiger, and he said, well, but the convection's there, so it's really, I mean, if you got magnetic fields, you got magnetic fields. Sure, the convection might not be the right amount of lobiness, and the eddies are not quite what they should be, but so is Regos and Taut wrong? I'm not saying wrong, I mean, that's a big word, but is that theory applicable?
I don't think so, because I think if you have this further amplification on longer time scales by the dynamo, then actually, if you eject the envelope, there will not be enough material anymore. So this will actually expand and freeze up. So I don't think that actually you would expect a strong dynamo effect. We don't see any. I mean, if there's any, we should have seen it in our box.
Are you sure?
Well, I mean, we measured the magnetic field, right, and it didn't change any much more anymore. Now, of course, you could argue, well, this happens on much longer time scales, but these time scales, probably you don't have these time scales, especially if you actually include a recombination effect. This was not included here, but if you have that, then of course you expand the image rather quickly and expel it, and you may just not have enough time to make the magnetic field strong. But that's actually sort of a simulation you still have to do that includes recombination and magnetic field.
I wonder if you can a little bit clarify the convection. So I'm just trying to understand. I little bit missed from the paper as well. So do you see the convective eddies themselves, or you just say that there is a convective instability?
Well, we say there's a convective instability, and actually you sort of see the I mean, you're talking about the convection that's actually introduced by the shear instability, right? Not the initial.
No, I wasn't talking about the initial instability.
Well, in the initial instability, we do see that, and actually.
So I just wonder if you can comment on the size of convective eddies as compared to the mixing wave theory.
Well, I mean,
how big are they?
Right, so we see the largest eddies. So this is actually sort of comparing an initial setup model where actually we mapped according to our mapping procedure so that we retain the convective structure. That's the right-hand side model. Here we suppressed it actually by changing the difference between the two gradients. And actually, you see the largest eddies here, and that's the pattern. I think Sebastian also compared the convective turnover times. I think they did not completely match, but I would have to look that up again. But at least you see that the envelope is convective. And how well this is resolved, that's of course still the question. I'm also not so sure whether, I mean, in the end, if you do after the plungent phase, you quickly develop this spiral pattern, and then actually this gets convective. I'm not so sure whether the initial convective pattern really plays such a role.
Well, actually, to be honest, I was extremely excited to read that you can see convection when the paper was out.
Yeah.
So my worry is that what we all could not get a proper energy deposition where it should be at the very beginning because we don't have proper viscosity, and proper viscosity is coupled with the convection. So I just was wondering how well the convection can be moved now.
Well, the largest eddy is roughly the convective pattern, but and the question is also, I mean, you could perhaps argue that it's the largest eddies that actually carry the energy away efficiently, right? So that's what you need to resolve. So I think the idea that was sort of argued yesterday, that you actually want to see the onset of the turbulent cascade, that should be enough. Because in the end, in the turbulent cascade, actually, you actually mix completely in one large eddy turnover time, right? So that should be sufficient.
But I guess I should point out, you don't have radiative losses.
That's right.
Right.
Well, I
Well,
think
for
with
all
this
mass stars,
was,
that is not important.
but this
Well,
was
I
done
mean,
with
you
the
can't
population.
lose energy.
Yeah.
So the convection can only just put it into something that can be used.
All right. Well, maybe some time off this must be some expectation. All right. So Logan, we talk next. Whoa, Flavius.
Those of you that don't know me, I'm Logan Prust. I want to thank you guys for having me. It's
Logan, can you use the mic?
Oh, yeah, sure.
But then there's other, I guess, approximation of the analytical that may not have.
Well, so I mean, your shear is on a certain scale, right? It could be
Yes.
higher if you were better resolved.
Yes, I guess you could measure that in He takes, I think, analytically they take the ultimate shear, which is the velocity and this is the gas. But of course, then it doesn't drive all the gas rotation instead. So you might overestimate.
All right, well, you want to try this thing?
And I think
Hello?
this is a very low shear.
Hello? Okay, oh, there we go. All right. All right, we all good now? All right, like I was saying, I want to thank you guys for having me. This has been a good opportunity for me to form collaborations and learn more about the field. So I'm going to present some of the work that I did using Manga with Bill Chang. All right, so what is Manga? So Manga is a moving mesh module that we've developed for Changa, which is an SPH code. And so Manga isn't really a true acronym, it's just moving mesh Changa. And one of the nice things about it is that although it's a moving mesh code, you can revert it back to SPH mode, and then if you turn off the moving part of the moving mesh, you get a static mesh. So you can use several different numerical methods with this code. For parallelization, it uses the Charm++ language, which allows it to be very scalable. And for computing the Voronoi mesh, it uses the Voro++ libraries, which allows it to directly compute the Voronoi tessellation from the mesh generating points, rather than first computing the Delaunay tessellation and then computing the Voronoi mesh from that. We've also recently developed a multi-stepping algorithm that we've implemented, and it offers speedups of 4 to 5 times over universal time stepping, which is nice because you want the code to run on a time scale that's less than the time scale of your PhD. And so we've, of course, implemented an ideal gas equation of state into Manga already, and we've also implemented the Mesa equation of state, which includes recombination energy. More on that later. And we've tested it on several test cases, some standard problems in fluid dynamics, and have shown that it matches up well with the SPH results, except that it better resolves the shocks. And then it's also been applied to a star and hydrostatic balance and a stellar merger. Okay, now onto the actual common envelope stuff. So for our simulations, we used initial conditions that seem to have become somewhat standard. 2 solar mass red giant, 1 solar mass companion, and I have to thank the other speakers for going through how the initial conditions for the giant are made. Make the star in Mesa, you get the entropy profile, construct an envelope with the same entropy profile, and then we can damp the spurious velocities that we get in Manga and show that the density and temperature profiles that we get do indeed faithfully reproduce what we get from MESA. And then for the companion particle, one solar mass dark matter particle, we put it right at the surface of the giant in a circular orbit, so 0 eccentricity to start off with, which, as we've talked about, may or may not be realistic initial conditions, so we're working on getting a more realistic model for that. We use a simulation box of 23 AU with periodic boundary conditions. By the time we end the simulation, the outflow doesn't get anywhere near the boundary, so we don't have to deal with problems with that. 800,000 particles. And then we do 2 different cases of rotation of the giant, 0% rotation, and then 95%. And the way that we do that is using the method of Morgan. We include a low density fluff outside, high temperature, and then I guess it's not an initial condition, but the smallest time step that we achieve in the simulations is about 2.5 seconds. All right. Didn't want to deal with embedding this, so I'll just slide over to it. All right, so see some pretty pictures. All right, like usual, plus marks the core, X marks the companion, so let's see what this thing does. This is with co-rotation. So we see initial plunge in where it ejects a large tidal tail there and unbinds a lot of mass, and then they're going to spiral in more slowly, and we'll see another larger tidal tail ejected around 75 days here. You know, there it goes, and we'll be able to see those tidal tails when we look at the plots of the unbound mass. I think there's another one, another smaller one coming up there. Yeah. Okay. So things will continue to spiral in more slowly, and we end with an eccentricity of about 0.1. We run all the way to 240 days. The plan was to run to 120 days to match Ullmann, but interesting stuff was still happening when we got to that point, so we decided to go to 240. All right. Okay, so you saw this plot earlier of the orbital separation, and then to make it a little easier to read on the right there, we smoothed it and put it on a log scale. So we find that with co-rotation, we get a final separation that's about 0.4 solar mass greater than without, which kind of makes sense because you're including additional angular momentum. It is possible the separation might still get significantly lower after 240 days, but we're getting dangerously close to the scale of our gravitational softening lengths at this point, so it might be dangerous to run farther. All right, so here's the money plot, the fraction of our envelope that's unbound. So we include recombination energy, and we find that doing so unbinds 60-some% of the envelope in both cases, a little more for co-rotation since there's that extra kinetic energy. We do find, though, that if we don't include, well, okay, first of all, I should say we're defining unbound mass as total energy greater than 0, total energy including potential, kinetic, and thermal energy. If we don't include internal energy, it gets much lower. We only unbind about 8% by the end. So this indicates that the treatment of the internal energy is very important in determining how much of the envelope is unbound. And on the right there, you see a density slice. It's at t equals 15 days, I believe, one of our simulations, and the black boundary there encloses the bound mass. Right? So you see the tidal tail there is unbound. All right. So, some conclusions, I've already said some of this. When you include co-rotation versus non-rotating, it results in a larger orbital separation and mass ejection, both of which you might expect because you're increasing the energy and angular momentum present. We've also found that the internal energy plays a large role in unbinding the envelope. So we might need to include radiation physics if the energy is not. If the energy from recombination is radiated away, it would make a large impact on how much of the envelope is unbound. And then we also may need to change our treatment of the gravitational softening so that we we can run farther if our simulations get to a lower separation. But as Luke was talking about, it can be non-trivial to do that, since it would change the gravitational potential energies and such. All right, I think I am under time, so I will be happy to answer any questions.
We have plenty of time for discussion. Fritz, you have your hand up first. Yeah. So you've shown these plots that actually had the projected density and only one which had a cut in the XY plane. So if you actually do a cut in the XY plane and later phases, do you also see the sort of Kelvin-Helmholtz instabilities in this? Do you check that?
I don't think we were able to resolve the Kelvin-Helmholtz instabilities, no.
You don't?
Okay, so we might, we haven't looked.
You haven't looked.
That's the answer. You got to do a slice,
Yeah.
projection, right? Yeah. We've done projection.
Well, there was one slice, but I think that was still too early to see. I mean, this was just 15 days, the slices you showed, right?
Yeah, I have done some other
They're
slices.
all projections, they're all projections.
Well, I've done some other slices too, although they weren't shown here, but I don't recall, I don't think we could resolve the Kelvin-Helmholtz instabilities though.
So I have a question. This is actually more general question for people who do SPH and moving mesh simulations. So there's been some debate here of whether the internal energy how much it contributes to the unbinding. Have you tried taking like some early time where you have cells which are, according to the mechanical criteria, bound, but with internal energy unbound? Just remembering who those cells are, plotting them sometime later, seeing if they're bound or unbound. And this will be good for SPH. Moving mesh will be kind of a fudge because you just affect a bit, but this will give you some handle what percentage of mesh was unbound because of the internal energy. Have you tried doing this?
No, we haven't tried that, but that's a good idea.
I think you have to be careful because like if there are enough mass fluxes that it doesn't really work with moving
Right.
mesh. So, but you can add tracer particles.
Right.
Yeah, I agree.
Yeah.
So I'm curious about your multiple tidal tails. That's something I haven't seen before. Do you have an idea what's causing that?
No. That's the short answer.
I think it's the core to secondary mass ratio. So like, is your secondary much lighter than the combined other star, or are they about the same? So you see this like in Ursula, where in Ursula's group they varied the mass ratio. You see it emerge when the
Changes
core
the
and the
amount of
secondary are similar. Yeah.
Okay. Yeah, thanks.
Questions, comments? Yes.
But we also compared models with and without recombination, right? And did they show any difference? Can you go back to them? So I'm not talking about including or not including the energy, including the actual putting the recombination in the simulation or not.
So you're asking about different equation states, yeah?
Yes.
Okay, so we are not sure, short answer, right? About adiabatic equation states. We need to study that a little bit. This is why it's not included, because that's what we're talking about.
You did run simulation without recombination.
We did run simulation with adiabatic equation states. So we don't trust it.
Just, sorry, very, very quick comment. We really have to make a distinction between something changes when you use the tabulated versus ideal equation of state. We know that that's true. We've seen it in all codes. And then the other side is how you define unbound. Do you use or not thermal/internal energy? And actually, there is a difference between thermal and internal when you go to tabulated equation of state. And you can try that by declaring your material unbound. First, you do the strict mechanical energy only, then you can add your thermal, and then you can add your internal. And you will have more and more unbound material.
Yeah, but initially, nobody should add recombination energy because it's a potential energy which has to
Indeed,
be
absolutely,
triggered, and
absolutely. So that's a
completely
big no-no, but I can
out of
see.
logic to add it initially. I mean, just nobody should do that.
Right, so please, when you write up, explain exactly what you mean by thermal, internal, what's in it, because it's not always so clear, right? We intend different things.
Yeah.
Yeah.
that partition may not be so easy with the basic equation state. Maybe who someone who makes the extra conjecture.
State explicitly with which quantity from the equation of state you use, right?
Yeah.
Well, I mean, like, they just give you the internal energy. I'm not sure the.
You might actually have to look at the code.
Yeah.
Yeah, I mean, the documentation is,
Yeah.
lacking, but the.
Right, well, that's just mine, right?
Yeah, so you might actually have to look at what the code's actually producing.
But isn't it the most fairest thing to just do that according to the kinetic energy and leave all the other terms out and then?
Yeah,
just-
I think that, I agree.
Also, I should say that method doesn't have recombination energy included. It will be added when you go to the lower levels. So I mean, it's always important what's your zero level of energy. In the case of method, it's the ionized state is where you started. So if you go to recombinant state, when the energy is added, it's not vice versa. So when you calculate initially ionized plasma,
Yeah.
the recombination energy is not in there. It's when
I
you
see.
do the delta
Okay,
E
so-
for energy, then it's added up.
I see, okay. So in fact, the answer is, that's actually without recombination energy.
Yeah, I mean, right, whether something is unbound or bound
Yeah.
really has to do with its bulk kinetic energy, period.
Yeah.
Period. And
Whether in
the
the
other stuff is all potential to do work.
Right.
But it is not whether the stuff is on an unclosed orbit. And I think that's, what we should be using as a baseline criterion for unbound.
But I mean, the product I've shown that Sebastian did with this very long-term run. I mean, this actually was the kinetic energy only and was run for 6,000 days or so. And you get a pretty complete ejection, assuming, of course, that you can use all the local energy deposition, right? So that's still the assumption.
Right, yeah, well, that's a big assumption, yeah.
course.
Yes.
Yeah. But I mean,
But it's
even,
not the fault.
even if you could use it, right, again, to use all of the internal energy, you have to cool to absolute zero. So, I mean, that's obviously not
Well, okay,
possible.
so that's not completely fair, right? So you want to use basically some fair fraction of the internal energy, right? So you don't have to cool it at absolute zero, right? If you're at 100,000 degrees, you cool out 10,000, that's 90% of it, okay? You're there already, okay? So that's not completely fair.
That's 90%, but I mean, that translates into a very large difference in the amount of unbound mass.
Well, that's like.
Right, depends on how close to that threshold the mass elements are.
Right, I mean, like, that's an expansion in a factor of maybe 3 in terms of spatial, and density decrease about a factor of 30, right? That's easy, that's easy, that can be captured. That's not, I don't think that's a big deal.
Well, I guess another way of looking at it would be, so internal energy really doesn't help an individual mass element become unbound. It helps other mass elements adjacent
Yes.
become unbound because it does work on them.
Right.
And so if you've got material that's on its way out, that's got a positive energy mechanical plus potential, and it does additional work on its surroundings,
Yes.
it may not matter at all.
Right.
Whereas, let's see, this is going the way I wanted to.
No, I think
Yeah,
that's
no,
right. I
I
mean,
mean,
another
like,
way to put
so
that,
the-
right, is
yeah.
that like the Bernoulli constant
Right.
is defined along a free streamline. And I think
Yeah.
what we're hearing here is that there's not necessarily a lot of free streamlines once
That's
you
right.
have a big mess, right?
Right.
Like-
So if you make the argument that like the Bernoulli integral is what you care about, right? And stuff comes out, right? For adiabatic winds, the Bernoulli integral must be positive even before it hits the starting point, right? And the starting point is basically where it escapes, essentially. Okay, so you use that criterion, basically say, well, like the wind doesn't escape until its starting point. You actually use the Bernoulli criterion, well, it escapes as soon as basically it's positive, right? And it's gone.
Well, it tells you what its local, for example,
Yes.
parameter is, but
Yes.
it doesn't tell you that it will make it to infinity because it might run into something else.
That's right,
Yeah,
exactly.
But
And
Bernoulli
that's
is
the
even
problem.
worse because it doesn't include internal energy, it includes enthalpy, which is even like a bigger term.
I understand, yeah. But it's the
But-
integral that Paul is discussing,
Yeah,
right?
but to speak about the flaws, this is what I see when I have recombination outflows. I mean, you have established those flaws which are just gradually evolving, and I didn't estimate it from the enthalpy point of view, but it's exactly how it should be. I mean, because they just constant for the time
Yeah.
Yeah,
being, et cetera.
I think enthalpy is
definitely an improvement, I think, because it's more of a measure of what's useful work.
Yeah.
But it still doesn't tell you whether that work will be expended, or that will be used to do work.
What's the typical
Or
cooling?
where?
Right, yeah.
Yeah. What's the typical cooling time?
I'm not the analyst, so I actually don't know.
If they're big enough, then
Yeah, yeah.
you
Yeah.
cool it only in the outward where you already, the
Right,
density is
the-
low,
the-
you won't do
the-
any work.
The question is basically, where the question combination of optimal depth, cooling time, and dynamic time. Right? So that's the thing which we have to consider.
I think there's no the current cooling prescription. If you really use them, then you will find for this common envelope, their cooling time is so short at the boundary. Maybe it's only 1 second. So, for example, if its cooling time at the edge is 1 second, that means if you go into 1,000 optical depths into that, from that layer go into that, and that means this layer cooling time is approximately 1,000 seconds. If
It doesn't feel linear.
No. If you cool from ionized state to molecular state, it become optically thin. Then you go to the next layer, and progressively into more deeper place. It
I
cools
would say
in-
the really short cooling time represents the fact that you're out of equilibrium if
Yeah,
you
yeah,
were
yeah.
to include cooling,
Yeah,
because
yeah.
then the cooling time would match the heating time, and you would be. So
Yeah,
like when
yeah.
you see a like tiny cooling time, that means, oh, if I were including that term, I would never arrive at this solution for
Yes.
the thermodynamic quantities.
Yes.
I just want to say this reminds me of the
Schumann times.
accretion disk literature, the radially inefficient accretion disk
Right.
literature, where people forever, and I'm not even sure it's ever been completely satisfied as to whether the outflows are actually unbound, or whether they're just
Right.
enormous convective eddies, and people are arguing.
Any other comments, questions?
Well, I mean, actually,
Yeah.
I think maybe there, I don't know exactly how to do this, but I mean, if you have, let's say, material that's all heading out, right? And it has a formally positive energy mechanical plus potential, then I think it's reasonable to say that absent any other assumptions about the interstellar medium, it's unbound. So I think maybe it's not just the value of some combination of the energies, but also the geometry of the flow that allows you to say, whether material is bound or
I mean,
not.
that's like, it's almost like strong equivalence and weak equivalence. I think there's a strong unbound condition is that, is that. But I mean, the thermal energy, I'm hesitant about not including it, because it is the potential to do work. You just don't know whether it's going to do its work. But the fact that it's there and available, I mean, you can't have a star that has more thermal energy than potential energy, and these
Stable, right, and it'll expand, right, yes, that's why.
So it's
that's
got to
true.
enter.
Yeah,
that's true.
Yeah, no, so it seems like ignoring thermal energy, not including this, if you're, you're trying to understand the initial state doesn't quite make sense, because it is a potential pressure gradient in some sense. Once you disturb it, you've got thermal energy there that may be useful for pushing things out, which is what you're really asking the recombination. You're going to invoke the recombination to happen once it cools, to now give you a new source of thermal energy, right? 'Cause that's all it does.
Yes,
The
because
recombination
thermal
energy turns into thermal energy, turns into pressure gradients, which
Yeah.
is the same thing as what you're asking for, with the thermal energy. So I'm not sure it's like ignoring the thermal energy in your initial description of what's bound and unbound makes sense either, because it will be available. Once you disturb the initial equilibrium, that's thermal energy that could be available to push things out.
My view is there is a strict criterion for unbound. Actually, the strictest criterion is, does it leave?
Yeah.
All right, that's
Well,
later.
let's put it together.
It's a lower limit on absolutely being certain of anything.
I think when you just have thermal energy, you don't know how it's going to redistribute it. It could decide to give
Right.
all that energy to one particle, or could
Well,
share it in some
okay, so
equitable
run into
fashion.
something,
That's also true, that's also true.
But I mean, it sort of common sense is that it will, you know, push some out and some will stay down.
So the universe works on democratic principles, not the 1%, generally.
It's full of mechanisms that concentrate things like matter in one place, right?
Well, gravity is the one that works principles, right? So, first you gotta-
Yeah, so I think of course, I mean, one way to determine this would be to run the simulations for long enough to have everything
Yes.
converted to kinetic energy. The problem with that is that at some point the energy errors that you have in the
Right.
simulation become too large. And that actually sort of prevents us from going much longer than I've shown in the plot, right? I mean, then we get to energy errors of like 5 to 10% and still like, I mean, the binding energy in the envelope that's still left there is not of that order.
Right.
So that's actually sort of, we can determine sort of like 80–90% of the envelope is ejected by that criterion, but that's about it.
Well, I think so.
That's another frontier on the numerical side that was not so much emphasized under large scale is actually how to handle the energy errors. And for the grid codes, it's probably mostly because of the coupling between the drug exposure and the hydrodynamics, right? So that's actually the largest uncertainty we have there. And that's also something that we should add to the list of the frontiers.
Right.
So we don't run simulation to the infinity, as well as anyone else, but what I found is that, I mean, it's really hard to find an adjunctive which will be just marginally unbound. In fact, if it will be unbound, then the kinetic energy will be much larger than the thermal energy that it has at that moment, and it will be not just like exceeding the, like, by tiny fraction of what will be criterion for unbound. So I don't think that we're doing too bad in general. I think that because nature doesn't like the perfect fine tuning, so we're fine.
So,
The perfect fine tuning will be a problem.
so let's just call the discussion now, because I think